Hi all, this is lecture 17. This is on section 8.1 on arc length. So what we want to do is we want to start using our integrals to be able to find things for us and to be able to calculate things. And so the first thing we can use integrals to find is the arc length. So if we think about a curve y equals f of x over a closed interval from a to b. So let's draw a picture here. Let's think about an interval from a to b on which I have a function. So a to b, and we're going to have a continuous function here. And what I want to know is what's the length of that curve. And the way that we do that is that we break this up into little sections, right? You can see the pattern already about what we do with integrals. And we're going to create little sections and we're going to say, okay, well, I can find the line between the two, or the distance between those 2 points. And I'm going to keep doing that as I go along. And you can see how that, especially if I take very, very small, infinitesimally small sections, little line segments, that I can pretty well capture the length of that line, okay, the arc. So how do we do that? Okay, well, what we want to do is we want to find the distance from one point to the next to find the length of each line segment. Well, the distance formula, the distance between 2 points, x1 and x1, y1 and x2, y2, is the square root of x2 minus x1 squared plus y2 minus y1 squared. And so what you're going to do here is you're going to say, okay, well, if each little line segment looks like this, then what I'm going to do here is I'm going to factor out x2 minus x1 squared. So I can do that. I can force factoring that out. And what's left is 1 plus, and in order to factor it out over here, I'd have to divide it. So we get y2 minus y1 squared over x2 minus x1 squared. Okay. Well, what we have here, if you bring out this first piece, the x2 minus x1 squared, bring it outside the square root, that leaves us with 1 plus something squared, right? And that something is y2 minus y1 over x2 minus x1, and that's the slope of that line. So if we think about the slope of that line as the derivative of my function goes in there. And what's on the outside is x2 minus x1, which is really like my delta x, right? And so if we do that and we take the limit essentially as our line segments go to 0, then this becomes the integral of the square root of 1 plus f prime of x squared dx, right? And so that's exactly what our arc length formula states. So if we have a continuous function on a curve from a to b, then the length of that curve is the integral from a to b of the square root of 1 plus the derivative of f squared dx. Now, you can see right away that when you have the square roots of something, we know that trig sub often ends up being the integration technique for things that involve square roots. So you can see how these might get messy really quickly. So we're going to try a couple of different techniques in simplifying things, and hopefully we'll be able to integrate. So example 1, we're going to find the arc length of the curve y equals x to the 3 halves between the points 1, 1 and 4, 8. Okay, so that means the length of the curve is the integral from 1 to 4, because I'm going to integrate with respect to x, so I want the x values. And we want the square root of 1 plus the derivative squared dx. And let's go over to the side and calculate that. So if y is x to the 3 halves, then y prime is 3 halves x to the 1 half. So this is 3 halves x to the 1 half. If I think about squaring that, then y prime squared is 9 over 4 times x. So this is really the integral from 1 to 4 of the square root of 1 plus 9 over 4x dx. And I can integrate this with a u sub. So if you let u, this is really a baby u sub, right? let this be 9, you can leave it the way it is. So 1 plus 9 over 4x. Then du is 9/4 dx. And dx is 4 over 9 du. So this becomes the integral of the square root of u times 4 over 9 du. And that's 4 over 9 times square root of u is going to become u to the 3/2 times 2/3, which will be, let's see, 8 over 27 times, and now I replace my u with my original 1 plus 9/4 x to the 3/2. And we're evaluating that from 1 to 4, so we bring back our boundaries at the end. Okay, from here we have 8 over 27. And when we plug in 4, the 4's cancel, and I get 9 plus 1 is 10 to the 3/2. And that's not a perfect square, so that's not going to be a nice number, but that's okay. And then we're going to plug in 1, so 9/4 plus 1, or 4/4, is going to be 13 over 4. Sorry, this is minus 13 over 4 to the 3/2. And that's messy, but it's correct. So if we were to figure that out as a decimal, that will give you the arc length of that curve. And our second example here gives our function in terms of y. And nothing changes here. This is exactly the same thing. So our arc length here is going to be the integral from 1 to 4, because my y value goes from 1 to 4, of the square root of 1 plus dx dy this time, squared dy. All right, so we're going to do exactly the same thing. And I'm going to kind of do this over on the side. I'm going to do the part that's underneath the square root on the side here so that we can figure out what goes under the square root. So if we have x equals y squared minus 1 over 8 times the natural log of x, and we take its derivative. So let's think about dx dy. That's going to be 2y minus 1 over 8. Sorry, hold on. We're mixing x's and y's, and that's because I typed it wrong. This should be a y right here. And that means that this should also be a y. Let's fix that. And so this should also be a y. So 1 over 8y. Okay, I'm going to have to square this. So the first thing I'm going to do is get common denominators. So this is the same as 16y squared minus 1 all over 8y. And then if we square it, that's going to become, let's see, so 16 squared, I believe, is 256. Y to the 4th minus 32y squared plus 1 all over 64y. And then I'm going to add 1 to that. So dx over dy squared plus 1. So I'm adding 1 to this. So 256 y to the 4th minus 32y squared plus 1 over 64y. And I'm adding 1, but I'm going to add it as 64y over 64y because I'm adding 1, so I want common denominators. So I have 64y on the bottom. And that's going to give me 256 y to the 4th plus 32y squared plus 1. And then that is factorable back as y squared, 16y squared plus 1 over 64y. And that's pretty common for some of these types of problems, where you're going to have a subtraction, and then when you add the 1, it changes it back to being adding the same number, which means that you can factor it as a perfect square. And so this whole thing is squared. So that's what I'm putting underneath my square root, right? So I can replace what's under my square root with that. So this is the integral from 1 to 4 of the square root of 16y squared plus 1 quantity squared over 64y squared. Right? Oh, nope, just 64y. Let's see. I feel like that's got to be wrong. 8y should have been 8y squared. And that would have been squared, and squared, and squared, and squared. Sorry about that. Those should all be squared. Okay, so that brings me back here. And we have 64y squared and then dy. Those are both squared, so I can get rid of the square root. So that's the integral from 1 to 4 of 16y squared plus 1 over 8y dy. Now I can split my fraction back apart. And that's just 2y plus 1/8 times 1 over y dy. And then I can find the antiderivative, which would be y squared plus 1/8 the natural log of y. And I'm evaluating that from 1 to 4. So you plug in 4, that gives you 16 plus 1/8 times the natural log of 4. Minus, when you plug in 1, that's 1 minus 1/8 times the natural log of 1. The natural log of 1 is 0. So that's going to give us 15 plus 1/8 the natural log of 4. So these can be a little bit involved. There's quite a bit of algebra usually, especially in the simplification. And that gets me something that I can put under the square root and take the square root of. So I'm totally okay if you go to the side and kind of work out what's happening with the algebra underneath the square root and then put that back into your integral. But make sure you show the work.